Okay, so I just want to welcome you all to this course, and I just want to check that if you were able to look at the syllabus on the canvas. Any questions on the syllabus? So this course deals with mechanical engineering systems. And what we are trying to do is we are trying to solve the problems where we not only look at a single component, but we look at uh, the whole system. So the way we are going to start is we are going to look at some simple systems, some simple components. Then we will see how these components work together. And at the end, we are going to look at how to design these different types of computers. I mean, these different types of components. And again, at the end, what we will do is we'll try to take a case study, something like an internal combustion engine, and then we will design components of the internal combustion engine. And also in last month, I bought a very small engine setup. Typically, we will not have time to do any experiments, but if you come to class, I can actually show you some demonstration of that engine working. And then I will show you what type of software tools that you can use to design the engine. So if we are able to do some just simple demonstrations, that's a very teeny tiny engine. I think it is about 12 cc. It runs on nitro. So you can run that engine indoors and you can actually perform some testing. You can get the data and then we can move on to correlating that data with the results that we get from simulation. The next thing is, I just want to ask you, how many of you are not comfortable with SolidWorks or Fusion 360 or any type of CAD program? Just please raise your hand in the because some of these homeworks are going to ask you to do some CAD modeling. So if you have used SolidWorks or Fusion 360 or any other CAD program, you can create those drawings using the CAD program. And if you come through the engineering program at Polytechnic School, we have a couple of courses that teach you how to CAD. If you don't have any experience, yeah, and SolidWorks will be fine. If you do not have any experience with CAD program, then what you can do is you can just create neat hand-drawn sketches. Now that brings me to another question, that there are a couple of assignments where I'm asking you to perform something called as finite element analysis. And what is this finite element analysis? The finite element analysis is basically you create a CAD program, and then, so for an example, if you have this pen, what you do is you create a 3D model of this pen. You want to find out what is the breaking point of this pen. So if you pull this, when would it break? So rather than actually performing the experiment, you can take that CAD model and import that into some sorts of CAM system, computer integrated manufacturing or computer integrated analysis, so CAE system. Apply the boundary conditions, apply the loads, and see what is the breaking point. You won't be able to perform the finite element analysis unless you have a CAD model. So, but please understand, when you go to industry, very rarely you are going to do paper calculations. All the design calculations that you are going to do, all the design, all the drawings, all the tolerancing that you are going to do will be done using a computer system. So some exposure is very critical. So if you haven't had the exposure to CAD, or if you haven't had any exposure to finite element analysis, please work on those assignments in teams. So for an example, let me ask you this question quickly. How many of you are familiar with SolidWorks? Please raise your hand. I see one. Anyone else? 2, 3, 4, 5. Okay, 6. Fantastic. How many of you have used some type of simulation or some type of finite element analysis in SolidWorks or in ANSYS? So 1, 2, 3, fantastic. So please team up with these students. So for an example, I think Alicia doesn't have any exposure to finite element analysis. Then please work with your classmates and work on those assignments together. I don't expect you to understand or be extremely proficient in CAD or finite element analysis, because that is not the real focus of this course. But when you go to industry, when you graduate and when you go to industry, you will never work out the design calculations by hand. You will start the design calculations by hand to just get an idea of what is the size. How would that component look? What are the approximate dimensions? But then finally, you will have to create a CAD model, import that into some type of computer system, and then run some type of analysis. So if you haven't had any exposure to CAD, if you don't have access to AutoCAD, or don't have access to SolidWorks, or don't have access to simulation software, ANSYS, or the Autodesk, or just the motion software, SolidWorks Motion, please work with your teammates. These softwares can be downloaded from my apps at ASU, but some softwares run on Mac, some softwares run on Mac and Windows. I know that SolidWorks only works on Windows. It doesn't work on Mac. So you will have to install either a virtual box or Parallels, or you have to use the boot camp to run the SolidWorks onto Mac. And then the problem is, if you have a Mac that is M1, then you can't just download the Windows. You have to download something, a different version of Windows. And I don't think SolidWorks works on that different version of Windows. So there are, I would anticipate some hiccups, some issues, but please understand, if those are beyond your control, your grade will not drop down. So just let me know that, hey, this is the problem, I'm not able to do it. So I'm going to recommend you to work with some other students. Just get yourself a little bit familiar with how the process works, and then actually team up on that part of assignments. Okay, that's all from my side. Will finite element analysis. I'm not gonna do motion analysis, but if you are really interested in motion analysis, I have excellent references. I used to do it previously, but then usually I don't. If I cover internal combustion engines, design of internal combustion engines, I don't get time to cover finite element analysis for motion systems. But if someone is interested, I can actually show you the problems that I worked out, or I can give you the references that give you step-by-step tutorial on how to work out the motion analysis problems in SolidWorks or motion analysis problems in design. However, we will create some nice animations. So you will see that when a particular joint, for example, a Cotter joint or a knuckle joint, that gets loaded, how would the contact get deformed, and how would that stress propagate, and how would it generate the stress concentration, and physically how would the component fail. But please understand, that is all extra. So it's not part of the core curriculum of this course. But at this point, I just want you to take a minute to read through the syllabus, which is uploaded on Canvas, and let me know if you have any questions. Okay, so do you want my video on or off? Okay, I'm gonna turn off my video. And so in today's class, unfortunately, class is going to be long, like all summer courses. So what I'm going to do is I'm going to give you some basic review material. We will review some concepts, and then we will talk about what are the design steps to design a Cotter joint, and then we will look at the design steps to design a knuckle joint. So let me start from the beginning. And this would be my first question that I usually ask. What is stress? Stress is load divided by area. Then what are the types of stresses? So the next question is types of stress. And there are two types. One is a normal stress and other one is the shear stress. So we have a normal stress and then we have a shear stress. Now, what do we mean by normal stress? The word normal means perpendicular. So what that means is the load is perpendicular to area. So for an example, if you have a component like this, and it is loaded with load P, this area A is perpendicular to the load P. So as you can see, load P is perpendicular to area A. Now, again, the direction would dictate whether that component is going to get stretched or it would be squished. So for an example here, clearly the load is going to stretch. So that means this is tensile. And alternatively, you can have the load load that could be compressive. So something like this. So this is compressive load. The equation for stress is sigma, which is P divided by A. Now, in this case, there will be an elongation delta. Here in this case, there will be a compression delta. Now, what do I mean by shear stress? So in shear stress, the load is parallel to area. So which is P parallel to A. Equation is the same equation, P divided by A. And then if you look at the way the component is loaded, the load would be like this. Now, what happens when you have the shear loading? So what I want you to do is, I want you to look at sort of this element which is over here. So this is the expanded view of this element. Under the load, you would observe that this element will get deformed something like this. So initially, the angle was 90 degrees. This will get deformed and the angle between the edges will no longer be 90 degrees. So shear stress causes shear deflection. So that is the angular change. So this is the change in the length and this is the change in the orientation. Now, if you think about the next concept, which is, you must have studied this or reviewed this in your previous classes. The next concept is strain. So what is strain? Strain is change in the length divided by original length. So for an example, if this length is L, then the strain that is given by epsilon is delta divided by L. Now, strain is a dimensionless quantity. So please understand, the numerator could be in millimeter, the denominator could be in millimeter. So the millimeter gets cancelled, and what you will have is, you will have a dimensionless quantity. But it can be positive or it can be negative. So strain could be positive or strain could be negative. Now, for the shear stress, there is concept which is called as the shear strain, that is given as gamma, which is the shear strain, and that is the difference between the initial angle, which is pi by 2, because those edges were perpendicular, minus the new angle, which is delta. And sometimes it again depends upon how you measure delta. So sometimes gamma depends. So here is what happens. So this is the initial element. And then what happens is, say after some time, this element gets deformed like this. So element gets deformed like this. So now this is gamma. And this guy is delta. So gamma is equal to 90 minus delta. The next important concept which I want you to kind of remember is the concept of modulus. So what is modulus? Modulus is nothing but ratio of stress divided by strain in elastic region. So what does that mean? So what it means is, imagine that you have this rod. This rod, it's pulled. Clearly, because of this pull, there will be some extension. And now you remove this pull. So initially you had some non-zero P, and after some time, you let that P go to 0. Then what happens is this rod will go back to its original shape. So this rod was in elastic region. So a common example is, imagine that you have this, think about it like you have this elastic or nylon band, and then you actually pull it. And if you let it go, it goes back to its original shape. So this was in the elastic region. So if you have sort of this elastic deformation, the load stretched the rod, you removed the load, it went back. So all that deformation was in the elastic region. But sometimes what could happen is, if you apply too much load, then this rod gets deflected and it stays deflected. So even if you let that load go, if you remove that load, the rod does not go back to its original shape. It retains that shape. In that case, that is the plastic deformation. Now, so in elastic region, the ratio of stress divided by strain is called modulus. So in the case of normal stresses, it is called as the Young's modulus. And that Young's modulus is given as E, and that is stress divided by strain. Stress is given by P divided by A, and strain is given by delta divided by L. So if you take out, you simplify, you are going to get delta is equal to P times L divided by A times E. So PL divided by AE, that is the equation for the deformation when the material properties are given. Now something else happens. So if you think about this rod, the mass of the rod is not changing. It's actually constant. In other words, for a solid rod, so if you pull, what happens is you get stretch in the longitudinal direction and you get squeeze in the lateral direction. So let's say initially this was the D, then this became D new, or the better word is D final. D final, this is D initial, and now this is L initial, and then this is L final. Oh man, lights keeps on turning on and off. Okay. So L final. So what I'm going to have is, I'm going to have a delta longitudinal Delta longitudinal is L final minus L initial. Delta lateral is going to be, again, it totally depends upon how you define delta. If you want to define the delta as final minus initial, I'm going to define this here as df minus di. But please understand, since the final dimension is greater than the initial dimension, this longitudinal value will be positive. Here, the final dimension in the lateral direction and the initial dimension in the lateral direction, it's reversed because the final df is less than initial di. That's why you have this negative direct sign. So what you have is, you got something called as mu, which is lateral divided by delta longitudinal. And this is a negative sign because please understand, this guy, no matter whether you consider it compression or tension, this is always going to be negative. And this negative with another negative gives you a positive value. And this value, which is called as mu, so mu is called Poisson's ratio. So remember, for an isentropic material, which means the properties are independent of direction. So for an example, if you have an orthostropic material like wood, then please understand, wood has different properties along the grain and perpendicular to the grain. But if you have the material like brass, brass or mild steel, then basically it would be an isentropic material. For isentropic material, you are going to need only two properties to define the entire material, which is Young's modulus and Poisson's ratio. Now, similar to the Young's modulus, if you extend the concept of Young's modulus to different stresses, like Young's modulus is defined for normal stress because load is perpendicular to area. If you extend this modulus concept to shear stress, you have something called as shear modulus. And that is shear stress. Shear stress is given by tau and divided by shear strain, which is given by gamma. So again, if you have shear loading, then you are going to have the shear stress. Young's modulus is also called as modulus of elasticity. And shear modulus is called as modulus of rigidity. So these are two different moduli. And if you look at the fluid mechanics, and if you study the properties of fluids or properties of liquids, especially for the liquids, there is a concept which is called as the bulk modulus. Bulk modulus. And bulk modulus is volumetric stress. What is volumetric stress? On liquids is pressure divided by the volumetric strain. So basically, change in the volume divided by initial volume is the volumetric strain, and pressure divided by volumetric strain is going to give me bulk modulus. So that is actually something that you can keep in mind is getting studying fluid mechanics and fluid mechanics properties. Any questions on the material that we have discussed so far? Now, next concept is what are the different types of stresses that we encounter. So no matter what type of stress you do, at the end of the day, those stresses would get resolved into either a normal stress or a shear stress. So whatever you do, finally you get those stresses. They are categorized as normal stress and shear stress. Now, one of those important stresses that you probably studied is something called as the bending stress. So consider that this is the beam. And on this beam, I'm going to show you a rotated cross section, which means this is the cross section of the beam. It's a rectangular beam. And now this beam is loaded. Once you load the beam kind of deflects. Once you load the beam kind of deflects. And as you can see, the bottom fibers are stretched and the top fibers are compressed. So because of this stretching and compression, you are going to have different types of stresses. So on top, you are going to have compressive stresses. And at the bottom, you are going to have tensile stresses. So these stresses, compression and tension, they are because of the bending. And if you were to plot these stresses, it shows a linear variation from the top to bottom. And then there is something called as this neutral axis. And at neutral axis, the fibers are neither stretched nor expanded. So in that case, you can we can actually state that neutral axis does not have any stress. And the fibers that are on the top of the neutral axis and the fibers that are on the bottom of the neutral axis, depending upon whether they are expanded or whether they are compressed, you have tension or compression. Now, next thing that we need to talk about is what is the equation for the bending stresses. Sigma is equal to M divided by I multiplied by Y, where sigma is the stress. Sigma, as we know, it is the stress. M is the bending moment. I is something called as the moment of inertia. And Y is the distance from neutral axis. So sigma is the stress, M is the bending moment, I is the moment of inertia, and Y is the distance from the neutral axis. So for an example, if I want to find out the stress at this location, this distance is going to be Y. And many a times we have to find out the values of I. So these values are either given in the tables, or if it's a simple cross section, for example, if it's a rectangular cross section, and this is XX, if this distance is B, this distance is D, then IXX is equal to B D cube by 12. If it's a circular cross section, and if the diameter of the circular cross section is D, I, whether you consider I XX, I YY, is going to be pi d raised to 4 divided by 64. Then if you have a hollow cross section, which is D outside, D inside, I is going to be pi by 64, D outside of the 4 inside to the 4. Now, if you have a composite cross section, then you will have to use something called as the parallel axis theorem, or in many cases, the easiest way to do that is look at the table or look at something called as the design data book, and you'll hear this a lot. Design data book or machinery's handbook. And they will have a lot of this design data given to us. Now, next concept that we actually talk about is the concept of torsion. So consider that this is a shaft. And then instead of bending, we are twisting it. So what is the difference between bending and twisting? So let's try to identify the coordinate system. So this shaft has 3 coordinates or 3 axes, X, Y, and Z. So the force that is around Z axis, so which is causing the Z axis to twist, this is actually the twist or torque. If T is the torque, and because of the twisting, you are gonna get the shear stress. Tau is equal to T divided by J multiplied by R. So again, the equation for torque is force multiplied by distance. So torque is force multiplied by distance. But since it is about an axis, typically this is considered as radius. And for bending moment, again, the equation is force multiplied by distance. But since it's a translational distance in the X or Y direction, it's usually kept as a distance. So for torque is like force multiplied by radius, and moment is force multiplied by the distance. And what is this J? J is called polar moment of inertia. What do we mean by polar moment of inertia? So think about XX and think about YY. So you have IXX and you have IYY. Those are about the X and Y axis. So those are just moment of inertias. But J is nothing but IZZ, which is IXX plus IYY. And typically, when we look at twisting or when we look at torque, what we do is we use circular cross sections. I mean, it's possible to study the twisting behavior of rectangular cross section, but typically it is out of the scope of undergraduate courses. If you go to the design, advanced design courses, you can actually look at the design of non-circular shafts. But for circular shafts, it's J, and J for circular shafts, if this diameter is D, J is equal to pi d raised to 4 divided by 32. So please understand, I is pi t to the power divided by 64, and this is IXX. It's same as IYY, and now IYY. Now J is IZZ. So please understand, IZZ is equal to pi d raised to 4 by 64. And there are two of these. So you get pi d raised to 4 by 32, because IZZ is equal to IXX plus IYY, and IZZ is pi d raised to 4 divided by 32. Any questions on the material so far? You can type your question in the chat window or raise your hand and unmute yourself. Okay, now the next question that comes in my mind is, please note, we have the normal stress here. This is the normal stress. And we have the shear stress here. So if you look at the way we have discussed it, that they are working independently. So there is no shear stress at this point when the normal stress is acting. There is no normal stress when the shear stress is acting. What happens when normal stress and shear stress act together? And let me pose this problem something like this. And think about, like, say, if you have a force in the x direction, if you have a force in the y direction, these two forces are perpendicular to each other. So which means the angle that is made is 90 degrees. So you understand that once we have f of x, f of y, they are perpendicular to each other. What you get is you get a resultant force. And we know what is the magnitude, which is the hypotenuse, f of x square plus f of y square. And that gives me the resultant force. Now, same thing, please understand, normal stress and shear stress, they are sort of perpendicular to each other. It's not exact, but think about it like, if I want to extend this discussion to normal stresses and shear stresses, they are perpendicular to each other. Now, what that means is you're gonna get a resultant stress. But unlike one single resultant stress, you get something called as a principal stress and you get maximum shear stress. So what it means is normal stress and shear stress, when they act together, they give rise to a bigger normal stress. And that bigger normal stress is nothing but principal stress. When normal stress and shear stress that act together, they give rise to a bigger shear stress. And that bigger shear stress is nothing but maximum shear stress. So if you have the resultant, if that resultant is resolved in the normal direction, it is called as the principal stress. If it resolved in the shear direction, it is called as the maximum shear stress. So principal stresses come into existence when normal and shear stresses, they act together. Now, this is an interesting question that I want you to think about, is what would be the principal stress if the shear stress is 0? And the most logical answer to that question is normal stress, because if the resultant of normal stress and shear stress is principal stress, and for some reason the shear stress is 0, then normal stress is equal to principal stress. And that exactly this equation talks about. Sigma P, there are two types of principal stresses: maximum principal stress and minimum principal stress. And if you, again, in the design, we are always looking at maximum. So what we need to do is, we need to do something like 1/2 sigma plus square root of sigma square plus 4 tau. That is the equation for principal stress. So let's, sigma is the normal stress. This is the shear. So if you think about it, substitute the value of shear stress is equal to 0, you'll get sigma P is equal to sigma. Now same thing for tau. Tau is equal to 1/2 square root of sigma square plus 4 tau square. So if you substitute sigma is equal to 0, shear stress, or this is shear stress max, is equal to sigma. So what are the cases wherein you would have normal stress and shear stress acting? So let me give you a simple example, very simple example, sort of if you think about it like a toy problem. Say you have a circular cross section, and on this circular cross section, say this is here, you have some load P. Now clearly this load is at angle theta. This load is at angle theta. So if I want to find out the stresses, I need to resolve these, something like P cosine theta, and then P sine theta. Now please understand, P cosine theta is perpendicular to area, and P sine theta is parallel to area. So what that means is if this area is A, so if this area is A, I'm gonna get value of sigma is equal to P cosine theta divided by A, and value of tau is P sine theta divided by A. And then I substitute these two values in the equation here to find out the values of sigma P and values of tau max. So you have sigma P and you have tau max. Now the question here is, the principal stress comes into existence, or tau max comes into existence, because normal and shear stresses, both these stresses, they act simultaneously. If they did not act simultaneously, then there is no way a principal stress can come into existence. There are some additional stresses that you should be aware of. So there are something called as complementary shear stress. So that shear stress is, again, as the word says, it's complementary. We didn't ask for it, but we just got it. So so complementary shear stress equation is SA y bar divided by BI. So again, if you are going to design something called as the leaf springs, or if you are going to design the composite springs, or if you are going to design the struts or composite struts, then you will see the complementary shear stress. So I'll just give you an equation for complementary shear stress. So there are, depending upon which textbook you use, there is the equation which is VQ divided by IT, or sometimes this equation is SA y bar divided by BI, say B. But depending upon which textbook you use, you will see these two equations. Typically, if you have studied mechanics of material in the United States, you probably have seen this equation. If you have studied mechanics of material or strength of material outside United States, maybe in Europe or in India, probably you have seen this type of equation. So again, but they mean this one and the same thing. V is equal to S is equal to shear force. Q is equal to AY bar, is called as the first moment of area. B is equal to T is equal to the thickness, or with the thickness dimension. And I, as you know, it is the moment of inertia. MOI stands for moment of inertia. And when we come to it, when we have to work out the problems, I would be happy to discuss these equations and then work out some of these problems for you. Now, I think with this background, you should be equipped to solve homework 1. And let me try to attempt some problems before I conclude the discussion here. And you're welcome to ask me any specific problems that you want some explanation on. Alternatively, I will just take out, or I will just study some simple problems that are given in the textbook. By the way, everyone got the copy of textbook. The good news is this textbook is available inexpensively on Amazon. This textbook, any version of textbook is fine. So if you can't find the latest and greatest version, but if you find an old version, that is totally fine. And the good news is, or good news or bad news is, there are answers given to some of those exercises. But please understand, those answers may be correct or may not be correct based on the assumptions that you have. So for an example, if a problem is worked out and your answer looks is say 40 millimeter, but the answer that is given in the textbook is 35 millimeter, there is a possibility that the answer in the textbook could be derived for different materials or different assumptions. So even if your answers look different than the answers given in the textbook, that does not mean your answer is wrong. So just be careful while following the textbook. So let me start with a very simple problem. So I have this joint, and this is the basic sort of the knuckle joint. And in today's class, we will look at the design of knuckle joints. But what we have is, we have a joint like this. So this is called as an forked end, and this is called as the eye end or the sock. And what you have is basically you have a pin. So something like this. And what happens is, here there is this pin. And this pin is, for the time being, think about it like this is one solid pin. And there is this load P. There is load P. Here, this cross-sectional area is circular. So this diameter is capital D, and the diameter of the pin is small d. So the question is, find, and I'm going to call this as rod, and then this is pin. So find stresses in rod and pin. So to find stress in the rod, please understand it's the tensile stress. So sigma rod is going to be P divided by pi by 4 d square. Now, if you look at the pin is having failures at two sides, 2 points. So pin can fail over here, pin can fail over here. So if this pin has to fail, this pin would fail in something called as double shear. And what it means is there are actually two areas resisting shear. So you have two areas resisting shear. So the shear stress tau pin is going to be P divided by 2 times the areas, which is pi by 4 d square. Everyone understood this? So if you have a knuckle joint, then you would have failure of the pin and you'll have the failure of the rod. Now let me take one more example. This is problem 1. And I'm going to take problem 2. So think about, like, this is a metal sheet of, say, thickness T. So this is a metal sheet of thickness T. And here there is a punch. So what does this punch do? This punch goes down, and as it travels, finally it comes in contact with this metal sheet, continues to go forward, and then basically it drops a blank. So think about it like if you were to punch a hole in the piece of paper, the circular part of the hole drops down. So this is called as the blank. And if the load on this punch is capital P, this is called as the punch. This is called as the sheet. So if the punch diameter is capital D, so when the punch comes in contact with the sheet, there is compressive stresses. But the sheet, if you look at the way sheet is going to fail, it's going to fail in shear. So if I want to find out the stresses in the punch, so sigma punch is equal to P divided by pi by 4 d square and tau blank or tau sheet. Please understand the resisting area is circumferential. So this is called as the circumferential shear, or also called as circumshear. So this is P divided by pi times T multiplied by T. And at any rate, if you look at the units are going to be Newton per millimeter square, because here pi is dimensionless, D has the diameter diameter in millimeter, T is in millimeter, so diameter square. So with that, you should be able to work out the problems that are given in homework. Any questions at this point? So after 1 hour 15 minutes, I have to, by issue policies, I will have to give you a break of 15-20 minutes. So I'm gonna give you all a break of about 15-20 minutes, and we will come back at 2:30. So if you want to grab a quick drink, go to the restroom, then we will see you again at to 30. So I'm going to stop here. So hopefully, with this information, you will be able to complete your homework. Let me go to the next topic on agenda is design of Cotter joint. Now, what is a Cotter joint? So if you think about it, let me try to draw a three-dimensional sketch of Cotter joint. So bear with me. So this is called as the spigot. This is called as the socket. And there is a hole, a rectangular hole in the spigot and socket. So this spigot goes inside and actually fits inside the socket. And then there is a cotter that goes down. So basically that cotter that goes down. So you have a spigot, you have a socket, and the cotter goes down. This is the rod. Again, we have the same rod over here. And these rods can have the same diameter or they could have a different diameter. Now, what are the typical applications of the cotter joint? So think about that when you want to transmit the forces in the X direction, whether compressive or tensile, you use cotter joint. And a classic application for cotter joint is if you have a steam engine. So if you have a steam engine, there is a piston, there is a cylinder, and there are valves, one at the inlet, one at the outlet. So there is valve 1, there is valve 2, and the high pressure steam can go from these valves. That would actually make this piston reciprocate inside, so it can go forward and backward. And this guy is called as the connecting rod, or also called as con rod. And this is attached to something called as the crosshead. So this is attached to the crosshead, and to the crosshead there is a crankshaft. So what you have is you have the steam engine. Now you want some easy way to separate out the crosshead from the engine. So this is the crosshead, and crosshead slides back and forth. The steam engine typically is stationary. So you are going to convert the reciprocating motion of the piston into a circular motion of the crankshaft. So this is crank. So this is crank. So to attach the connecting rod to the crosshead, this is where you would use a Cotter joint. So this guy is used to attach the connecting rod to the crosshead. Now there are different ways this Cotter joint can fail. Either the spigot end could fail, or the rod end could fail, or the socket end could fail. But please try to understand the failure modes will be similar to the stresses and failures that we have seen earlier. So the idea in design of Cotter joint is we look at the different cross sections, we look at the loads that are coming onto the cross section, and find out the best possible cross section, or find cross section dimensions that can support that type of load. So for design of Cotter joint, typically the problem statement would be something like this. Design a Cotter joint. Design a Cotter joint to support load P. And typically these loads are quite high and they are given to us in kilonewton. But for calculations, we will have to convert these loads to Newton, where the spigot and socket are made with some material, are made say with steel or cast iron. And the design stresses are sigma T, which is the design tensile strength. Sigma C is the design compressive strength. And tau is design shear strength. Now there is something that I want to talk about. What do I mean by design? So if you look at the way a mild steel specimen fails, so sigma divided and epsilon. So what we do is we plot something called as the stress strain curve. And the stress strain curve typically for mild steel it is shown like this. This region is the elastic region. So what happens in elastic region is the stress is proportional to strain. And after elastic region, this is called as the plastic region. And this is the point where the material fails. Now, slope of this line in the elastic region is called as the Young's modulus. So this is E. So slope of stress strain in elastic region is E, or Young's modulus. Now, as an engineer, we don't want to go inside the plastic region. So which means what happens, whatever happens, our material should not be loaded beyond this point. So this is called as the yield point. Yield means giving up. So once you cross the yield point, material yields. Yielding means material starts expanding, material starts giving up. So there is something called as the design stress, which is sigma design. So this is the design stress. So the design stress is always less than yield stress. And the ratio is called as factor of safety. So what is factor of safety? Factor of safety is ratio of sigma y divided by sigma design. And depending upon the application, the factor of safety would vary. So for an example, for typical engineering applications, the factor of safety could go anywhere between 3 to 4. If you have a mission critical operation where humans are involved, or basically the failure would lead to catastrophe or loss of human lives, then you can expand the factor of safety. And the typical values of factor of safety are given in the design data book or machinery's handbook. So if you have a particular application and you want to find out, hey, what is the typical factor of safety, then what you do is you go look at that application, and for that application, you say whether it is continuous duty, intermittent duty, or light duty, and so on. And for different duty conditions or different operating conditions, the factor of safety values would be different. Factor of safety, you think about it like sort of, it's like it accounts for engineering errors and assumptions. So one classic way is, if you think about it, that you get a material, that material has some impurities, that material is not perfect. So how would you account for imperfection in the manufacturing, imperfection in the material? And for that, you use a factor of safety. If you are confident that the material is homogeneous, continuous, no defects, no blowholes, no impurities, then you can actually go with a lower factor of safety. But if you get a material that you are not very sure of, maybe it's not very pure, there is impurity, then you will have to increase the factor of safety. But now this is an interesting concept, because for an example, if you are trying to design an aerospace component, then it's again, the failure is going to cost human lives. So you want to use high factor of safety. But if you look at the way the planes are designed, Higher factor of safety means bigger components, bigger weight, larger dimensions. That means you are going to spend a lot more fuel for performing particular operation. So again, you have to kind of optimize between the use case and the materials that are available to you. That's why aircraft components are super expensive. The reason they are super expensive because they are under critical tolerances. The manufacturing methods are under critical tolerances. The certification methods or refurbishment methods or even the assembly methods are under critical tolerances. So that's why the aircraft components are lighter, stronger, and significantly more expensive than automotive applications. For an example, just to give an idea, if you take a bolt that is used in an aircraft, the same M4, M5, M10, M12 bolt, if it is going to go on an aircraft, would be 10 times expensive compared to the same bolt that is used for a household application. And the reason for that is because the materials, the material that is used, the design process that is used, or manufacturing process that is used, it's critical because you can't afford a failure in an aircraft. And before anything goes on to the aircraft, the Federal Aviation Administration, FAA, has to certify that component. Even a simple bolt, even a simple housing, casing, no matter what that is, even the glass, the window, the reinforcement, the seat belts, everything is subjected to rigorous inspection and standard DOD or MIL standards before that component gets installed in an aircraft. And that is the reason why, even though there are so many aircrafts flying, taking off, so many airports, there are national airports, international airports, still you don't see failures, or you don't see planes crashing because of all these checks and balances that are placed by the legal authorities or by governments to make sure that the people's lives are safe all the time. So coming back to the point that factor of safety, sometimes it may be given to you, it may not, sometimes it may not be given to you. If the factor of safety is not given, then based on the application, you will have to go and select appropriate factor of safety. Sometimes these values of design tensile strength, design compressive strength, and design shear strength is given to you. Sometimes it's not given. And at that time, if it is not given, then you have to go back to the design data book and select the appropriate values for a design. So with that, if you work out a problem, either for the homework or for the quiz, the problem statement would be something like this: design a Cotter joint, which means find out all the important dimensions of this particular mechanical engineering system. Once again, why is this a system? This is a system because you have three components as part of this system. So what you have is, you have a spigot, you have a socket, and you have a Cotter. When this whole thing gets assembled, what you have is a Cotter joint. That's why this is a mechanical engineering system. And we are going to design this mechanical engineering system step by step. Okay, any questions? So step number 1. So this I'm going to call, let me use D. This is D. So step 1, design of rod. And the dimension is D. Now please understand, this rod is in either compression or in tension. So basically, if you look at the way this rod is going to fail, this is the failure area, which is pi by 4 d square. I'm going to assume the rod fails in tension. Rod failure in tension. So what we have is sigma t is equal to P divided by pi by 4 d square. Now please understand, the value of P is given to us. Value of sigma t is known from the design data book. Then the only unknown here is T, which would be in millimeter. Now some of you may ask me, why not to find D in compression? And you're absolutely right. Sometimes the socket and spigot, this joint would be in, Cotter joint would be in compression. But we are trying to find out dimensions that are always bigger. So value of sigma c is greater than sigma t. So for steel with factor of safety of 3, sigma c value is 100 Newton per millimeter square. Sigma t value is 70 Newton per millimeter square. So what that means, if I use the value of sigma t, my diameter would be larger if I were to use the value of sigma c. So the rod diameter is found out using tensile failure and not compression failure. Next, step 2. Now, step 2, we have to actually solve this problem in 2 steps. So I want you to consider this dimension, and I'm going to call this dimension D2. D2. And I'm going to call the thickness of the Cotter as T. So T is the thickness of Cotter. So if you consider the cross-section area here, the area is this. T and D1. So T and D1. The failure is also again in tension. So sigma T is equal to P divided by pi by 4. Actually, this is D2. D2 square minus D2 times T. So now here we have a problem. So check this out. The value of P is known. Value of sigma T is found out. But at this time, there are 2 unknowns. So there is D and there is T. So clearly, we can't find out 2 unknowns. with one equation. So we have to use one more equation. And I'm going to write that step on the right hand side. So this will be clear. So this is called a step 3. And if you look at the way the Cotter joint is, so you have this Cotter just sitting over here. Now, if this Cotter has to fail, so think about it that you have a load here. If you have a load here, if this Cotter has to fail, then this Cotter is going to fail in double shear. So Cotter fails in double shear. The other way this Cotter could fail is, now think about it like you're applying the compressive force. Then what could happen is the Cotter could crush. So what is going to crush? That this area, if you think about it, this area would crush. And what is this area? No, you don't have to make FM failure mode effect analysis chart. If you want to make it, that's good. If you don't want to make it, no worries. So the Cotter is going to be crushed here. So this is D2 and this is T. So if you look at the failure, this is going to be sigma C is equal to P divided by D2 times T. So now please try to understand. Again, here we have the same issue. We know the value of P that is given to us. We know the value of sigma C that is given to us. But this equation also has two unknowns. So if you look at this equation 2, and if you look at this equation 3, we have two equations and two unknowns. So solving step 2 and step 3 simultaneously, we should be able to find out value of D2 and we should be able to find out value of T. So with this, so we have to kind of do this simultaneously. Step 1 would be find the value of the product D2 times T from step 3, substitute that value in equation 2, and then find out the value of D2. The next part is the next step. Now, step 4 is socket tension or failure of socket along the slot. So now we are going to look at design of socket. So this guy is socket. So think about the failure which is happening here. Think about the failure that is happening here. Step 4, if you look at the failure mode, or if the way that socket is going to fail, it's going to look something like this. And this is the area that is resisting the failure. So this is D2. And if you want to find out what is the resisting area, that resisting area, and I'm gonna write this expression down. So that resisting area is sigma T P divided by pi by 4 times D1 square minus pi by 4 D2 square minus D1 minus D2 multiplied by thickness T. So I just want to tell you that value of D2 we already know. This value of D2 comes from step 2. So if you look at this entire equation, value of D2 is known from step 2. Value of T is known from step 3. Value of D2 is known from step 2. So the only unknown in this equation is D1. Because value of P is given to us, value of sigma T we can find out from the design data book. And once we substitute all these values, we are going to find out the value of D1. Next step, which is step 5. Which is, so this is the socket, tensile failure. Step 5 is Cotter shear failure. And so this is going to be double shear. Now, one thing I want you to understand is Cotter typically has a taper, and this taper value is specified in the design book. And what you have is you have curved ends in the top and the bottom, because what you do is you basically hammer this end so that the Cotter gets interference fit when it is holding the spigot and socket. Now, one important thing to keep in mind is, even though this is changing, say this is where the Cotter is failing, for the purposes of design, we consider the average width. So this width is basically B. And what we do is we find out tau is equal to P divided by 2 times B times T. So this is B1 and B2. But since the Cotter is tapering, this is an assumption So B, think about it like B1 plus B2 divided by 2 approximately. So we consider the value of B, and typically the Cotter would have 1:10 or 1:20 type of taper, and that taper is provided so that once you insert the Cotter and once you start hammering on the top, that Cotter actually can travel smoothly in the assembly. So that's why we usually provide a taper. So next step, after step 5, what you have is step 6. Which is socket collar crushing. So what happens in the socket collar is what you have. Let me give you this socket collar has an outside diameter D4. So sigma C is equal to P divided by D4 minus D2 multiplied by T. And you know, D2 is, as you know, is the diameter of the socket. Sorry, diameter of the spigot. D2 is the diameter of spigot. Spigot is inserted inside the socket. Then you tap the Cotter, but the Cotter can actually crush the socket collar. So this is the equation. So value of P is known. Value of sigma can be found out. Value of D2 from step 2. T from step 3. And from here, you can find out the value of D4. Step 6. Step 7. So socket end failure in crushing. So if you look at the socket, so, and I will try to show you what this means. And we looked at the same failure mode earlier, but at that time we looked at the different area. So this is the area that is actually crushing, and this is T. Oh, we socket and yeah. So yeah, actually I should have drawn this figure here. It's D4. This is D2. It's D. Now socket end in shearing. Socket end in shear. So if you look at the socket end in shearing, Uh, so the equation is tau P divided by 2 times d4 minus d2 multiplied by c. From here, c is thickness of socket collar. So you have the socket collar and you want to find out the thickness of the socket collar. So I just want to show you this failure mode because it might be difficult to visualize. So let me draw a three-dimensional view. And imagine that we have this Cotter that is sitting over here. And this Cotter slices this whole thing. So what's going to happen is you're going to have one piece that is coming out. You're going to have another piece that is coming out. And the failure mode is basically this guy. This is C. So this is C. This is D4. This is D2. So what you have is you have the shear that is happening over here. But please try to understand there are two areas. So one is over here and the other one is on the back side. One is area here, another area is on the back side. So you have these two areas. So that's why you have this shearing, which is again a double shear. That's why you have this 2 over here. Now, step 8. Step 8. So failure of rod end in shear. So if you think about it, the rod end is also in shear, and I'm going to talk about that distance A. So if you look at the failure equation, which is tau is equal to P divided by 2 times A times D2, and D2 is known from step 2. Value of P is given to us. Value of tau is known. So value of A can be found out. And this value of A is again because of the shear failure. Next step, which is step 9, is spigot collar in crushing. And spigot collar in crushing is nothing but this cross-section area. which is D3. This is D2. And this is sigma C is equal to P divided by pi by 4 D3 square minus D2 square. Here, value of P is given, value of sigma C we know, value of D2 we know from step 2. And from this equation, you can find out value of D3. Step 10. So spigot collar. So we say you can actually do a socket collar in shearing. So there is something else. So spigot collar in crushing. Collar in shearing. And we already did something like this. So tau is equal to P divided by pi times D2 times T. So if you think about what is happening is so this is D2 and this distance is T. So think about it like it's a circumferential shear. Let me show you. So this comes out from here. It just gets pulled out. So then step 11 is, oh, I didn't complete this discussion. P is known, tau is given, D2 is known. So from here, you can find out value of T. And in step 11, we have to find check Cotter for bending. Now, if you think about the Cotter could bend. And we don't want the stresses on Cotter to be significantly high. So what we do is we use the equation M divided by I multiplied by Y to find out the sigma bending. And sigma bending should be less than sigma tensile, because sigma tensile is less than sigma compressive. So this actually works. Now, the process here is really complicated. So let me show you what's happening here. So we have this Cotter. On this Cotter, what you have is you have different types of loading. So you have a simply supported loading or uniformly distributed loading here, and you have uniformly varying load over here. So these are the loads. on this Cotter. So the procedure is, for this loading condition, so these are the loads on the Cotter. Find out bending moment. So what is the bending moment considering the length of the Cotter? And again, these loads are not uniform. One is uniformly distributed, other one is uniformly varying. So what you will have to do is, based on the distribution of the load, you have to find out the maximum bending moment. This maximum bending moment needs to be substituted in this M, find out the values of I, and then find out the value of Y, and then make sure sigma is less than that. But this entire equation, and you can look at how the equation is developed in the textbook, this equation can be approximated to P D4 plus 0.5 D2 divided by 2 times T times P square. So, and please understand, that's why this is the last step, because if you look at all the previous steps, we found out the value of D4, we found out the value of D2, we found out the value of T, we found out the value of B. So you can substitute these equations, the values in this equation, and make sure that the Cotter is safe, which means the bending load in Cotter, or the bending stress in Cotter, is less than the tensile failure stress of the Cotter. And that's why this is the last step. If you really want to look at how this equation came about, then first, from the loading, you have to draw shear force diagram. From shear force diagram, you have to find out the bending moment diagram. And then you have to find out the maximum bending moment, and then you have to substitute the maximum bending moment in equation 11. And once that is done, most of the engineering steps are complete. There are some last few steps which they are from empirical analysis, like what is empirical relation or empirical values. So based on a lot of trial and error and experimentation, the engineers came up with certain values or the thumb rules. So even though there may be a scientific or technical basis for those thumb rules, or there may not be a scientific or technical basis for those thumb rules, but though they seem to work over last hundreds of years. So if you look at the textbook, they will give you these thumb rules or these standard dimensions, which are non-engineering dimensions. They come from either the proportions, they come from the ease in manufacturing, they come from because just it happened to be that this particular proportion is perfect, just like a golden ratio. So this is perfect, serving the purpose, working fine. So please look at the textbook for those empirical dimensions. And then at the end, you can draw a neat sketch of the Cotter joint. So let me quickly review the steps. So Cotter joint has 11 steps, and Cotter joint is used to transmit the forces, not torques, not moment, just forces. And you have to systematically go with step 1, find the diameter, step 2, work in conjunction with step 3 to find out the diameter of the spigot and the thickness. Then go to socket tensile failure, find out the diameter D1, then look at the Cotter shear failure, find out the width of the Cotter, which is B. Then you have to look at the socket collar crushing, then that will give you the value of D4. Then you have to look at the socket end shear. That actually will give you the thickness of the socket collar, which is C. Then you have to look at the failure of the rod end in the shear, and then that will give you the dimension A. Then you will have to find out the spigot collar crushing. That will give you the dimension D3. Then you will have circumferential shear on the collar. That would actually give you the value of D, the value of T, and that will actually finally, once you're done with that, you will have the socket collar for bending. So I just want to draw a nicer sketch for this. I didn't draw. So this would actually look something like this. So this is how it would look like. So that collar would just come out. And these are the steps for Cotter joint. There are a couple of variations possible. Sometimes you can have a double Cotter joint. What do I mean by double Cotter joint? Is you can have one end over here, you can have one end over here, and then there will be sort of a sleeve, and then there will be one Cotter over here, and there will be another Cotter over here. So the procedure is exactly same. And in that case, what you do is you follow the same procedure. It's actually easier in some sense. And sometimes what you have is you have a jib and Cotter joint. So this is double Cotter. Or you can have something called as the jib and Cotter. Or you can have maybe jib and Cotter for, or actually you can have the piston rod. So there is a one variation possible here. There is another variation possible in jib and Cotter. There is another variation possible in crosshead, con rod. So these are different variations in the Cotter joint that are possible. But the basic design steps are the same, but depending upon the application, there might be some changes here or there. Now, any questions? At this point, I wanted to see, would you be able to plug in the values, get the dimensions, and draw the sketch of the Cotter joint? Do you want me to solve any problem, or you can actually just follow the design recipe that I gave you and then find out, design the Cotter joint? There are about 5 to 6 problems completely worked out in the textbook for each different variety of Cotter joint. So if you have any questions, you can actually look at the examples that are worked out in the textbook. But this is the baseline procedure for Cotter joint, and that would allow you to design any variation of the Cotter joint. This chapter is chapter 12. So I'll just write this down. So chapter 12 from the textbook. Okay. Again, uh, time for a break. So we are going to take a break of 15 minutes, and then we will continue our discussion of the last topic of today's lesson, which is design of knuckle joint. So I'm gonna pause. Okay, so in this last part, we are going to talk about the design of knuckle joint. So can you see me? So knuckle joint is exactly what it means. It's a knuckle. So what you have is you have a knuckle. So something like this. And then what you have is you have a pin that goes throughout the knuckle, and that pin holds these two knuckles together. So if you look at the sketch of the knuckle joint, and there are some variations in this the joint, but I'll show you a basic design. Then here, and what you have is you have this pin that goes through this knuckle. So you have this pin that goes through this knuckle. And here there is a collar. So you have the the eye end. So this is called as the eye. This is called as the fork end. And here you have the pin. So if you look this joint in the front view, it's going to look similar to the Cotter joint, but what you have is you have a pin, not Cotter. So you have the eye end, you have the fork end, and you have the pin. And what we are going to do is we are going to use the engineering principles to design this knuckle joint. And This knuckle joint, believe it or not, is used in a lot of applications. For an example, a simple hinge, if you think about it, it's similar to a knuckle joint. So for an example, if you look at the hinges, they also have the eye end, they have the fork end, or they could have multiple fork ends, and they are attached to one another using this pin that is either could be tapped or held in place by some type of a joint method. So how do we design? Just like Cotter joint, we are going to design step by step, looking at different types of failures. And the advantage of the knuckle joint is it allows for articulation. So basically, the eye end and the fork end could have relative motion. And knuckle joint is used ubiquitously everywhere. So for an example, if you look at these power lines that are on the power road, if you look at the power lines on the power road, then usually you would see that there are ropes, and these ropes, steel rope, are attached to some type of a fastener on the ground. And here, basically here, you would see a variation of knuckle joint. So here you would see a knuckle joint. Even if you look at the hinges, hinges is one type of knuckle joints. So knuckle joints are used in a lot of applications, in automotive applications and even in other applications. So how do we analyze this knuckle joint? To design the knuckle joint, same thing. They will give us the value of load P. So P known, sigma T, sigma C, and tau, the design stresses, are known. Or given. If the design stress values are not given, you can actually look at the design data book and find out these values. Again, typically the eye and the fork, so this eye and the fork end are made up with one material, and pin could be made up with different material, or sometimes the pin is made with the same material as well. So either they will give you the material properties for the pin, or you would have to find out the material properties for the pin. And step by step, we are going to find all these dimensions. So let's start. Step 1. So rod dia in direct tension. So if you look at the rod diameter, sigma T is equal to P pi by 4 D square. Value of P is known, sigma T is given, so value of D can be found out. Then step 2, pin diameter, which is D1, pin in double shear, which is tau P pi by 4 D1 square multiplied by 2. And this 2 comes in the picture because pin is in the double shear. So if you think about the pin can fail over here and pin can fail over here. So the pin is in double shear. And from here, you can find out the value of D1. Step 3, you can actually check for the bending. So here you can also check pin for bending. Now this is also very interesting. If you look at the loading on the pin, this is the pin, the load profile, it's similar to a Cotter. So load profile is similar to a Cotter. So again, the procedure is you have to look at the load distribution and you have to find out the shear force. Then you have to find out the bending moment. So shear force, bending moment, that should get you the maximum bending moment. And then use the equation sigma is equal to m divided by I multiplied by y, where I is the circular cross section, which is pi by 64 d to the power 4, which is d1 to the power 4. And if you want to develop the equation, you can follow the procedure that is given in the textbook, or let me just give you the equation. Sigma bending is equal to p by 2 multiplied by t1 by 3 plus t by 4 divided by pi by 32 d1 to the power 4. And t1 is this distance, and t is this distance. So substitute these values and then find out sigma b, and this needs to be less than sigma t. Step 3, is I end failure in tension. So sigma t is equal to p divided by d2 minus d1 multiplied by t. So I just want to show you what we mean by I end in tension. So this is the I end. I want you to think about failure here. So what's going to happen is you will have a failure, which is something like this. So this dimension is d2. This dimension is d1, and this dimension is t. So this is the I end failure in tension. Already think about it. This d1 is the same as diameter of the pin. So this d1 is the diameter of the pin. So this guy is known. Then D2, typically D2 is approximately 2 times D1. And remember this sort of thumb rule all the time. Like if you have a boss means you have an inner hole, you have an outer hole, and you have something that is passing through the inner hole. So you want to make sure that this whole design is safe. So this outside diameter is typically 2 times inside diameter. Step 4. Eye end failure in shear. Now what happens when the eye end is failing in shear? So think about it like eye end and what happens is this thing comes out. So this whole thing comes out. So this again tau is equal to P D2 minus D1 multiplied by T. So you have to check, because one thing that I want you to understand, the denominator in step 3 and denominator in step 4 is the same. So if you find out the dimensions from step 3, you have to make sure that that end is safe in shear. If you find the dimensions from step 4, you have to go back and check the dimension in step 3. The next part is you have to find the eye failure. So failure of eye in crushing. And the eye end failure in crushing is something like this. So here we have this pin that is going through this. And this pin is going to crush against this. So if you look at the area that is resisting this crushing is nothing but the projected cross section. So sigma C is equal to P D1 times T, where D1 is the diameter of the pin or the inside diameter of the eye, and T is the thickness of the eye. Please note, D1 is known, T is known, so you can just check to make sure that this dimension is correct. Then next step, step 6. Fork end intention. Now, I want to ask you this simple question. For the knuckle joint, you have an eye end over here. And you have a forked end over here. So you have a forked end over here. Can you see that the forked end is approximately 2 I ends? So imagine that the failure that gonna have on the I end, which is the same type of failure. You would have a tensile failure, you can have a shear failure. So all these failures that we talked about over here. So I end in, so let's see. So I end failure in tension, I end failure in shear, I end failure in crushing. Same failures would happen on the forked end. But what is the difference? What is the difference? So the failures that we saw on the I end would happen on the forked end. The only difference is the areas would be multiplied by 2 times. Do you agree with me? Now, what is the implication? Implication is nothing is going to happen to the diameters, because if you look at the knuckle joint from top, you're going to have the forked end. So if you look from top, what you would see is you would just see something like this. So you will see something like this. You are going to have an I end and you are going to have a forked end. So these diameters are going to remain the same. The only difference is this thickness is going to be different. This thickness, so I will show you here, this thickness is going to be different. And if this thickness is, I'm just going to call T1, then what it means is T plus T should be equal to T1. Which means if you take the thickness of the I end, divide that by 2, you got the design for the forked end. But what we do is, just to be on the safer side, we actually make this T is equal to a little bit greater. So I would say T divided by T1 divided by 2 multiplied by, say, 1.3 times. So this is an approximate relationship that can be used to find out the thicknesses. And once you find this T, which is given, which is the thickness of the forked end, you would have to repeat steps 3, 4, and 5. 3, 4, and 5 to check. So how would you check it? So you will say checking forked end in tension, which is sigma is equal to P divided by D2 minus D1 multiplied by 2 times T. And this should be less than sigma T. Checking fork end for shear. Same thing, P D2 2 times T should be less than sigma. And checking fork end for crushing, and sigma C is equal to P divided by D1 times 2 times T should be less than sigma C. And that's it. So, and then what you do is you draw a neat and nice sketch for the knuckle joint. And then that is the design of knuckle joint. There is an alternate procedure that is given in the textbook. The procedure that is given in the textbook gives you standard dimensions of the knuckle joint based on the design data. So design data will define all these dimensions based on the principal dimension, which is the primary dimension, which is the rod diameter. So all these dimensions can be described as proportional to the rod diameter. But even though you get all these different dimensions, what you should do is you should show that your design is safe, which means once you find all these dimensions, just go step by step and check if your joint is safe. And that is how you would design a knuckle joint. Okay, with that, in today's lesson, we covered the basic material, we covered the design of Cotter joint, and we covered the design of knuckle joint. Now, at this point, I believe we have covered enough material for homework 1, homework 2, and quiz 1. So, but pace yourself and then just work on homework 1, quiz 1, and homework 2 step by step. And I would cover the next few lessons, few more designs on Thursday, and that will get you on track to work on the remaining homeworks and quizzes. So I'm going to stop here, but I would be happy to answer any questions you may have.